Hello, and welcome to this lesson on Avogadro's law and its application. In today's lesson, we will understand Avogadro's law and its significance in chemistry. We will also learn to apply Avogadro's law to find the volume occupied by 1 mole of gas at room temperature and pressure. So far, we've discussed fundamental quantitative concepts in chemistry, including the mole as a basic unit for counting particles and performing calculations. Building on this foundation, today's lesson will advance our chemical understanding by introducing Avogadro's law, which connects the amount of substance, in moles, to the volume it occupies. This connection is crucial as it allows us to predict and measure the behavior of gases in various chemical processes, enhancing our grasp of both theoretical and practical aspects of chemistry. Let's delve into Avogadro's law and its significance. Avogadro's law is a fundamental concept in chemistry. It states that equal volumes of gases under the same temperature and pressure contain an equal number of molecules or moles. For example, suppose you have 3 identical containers, all at the same temperature and pressure, where one has oxygen, 1 water vapor, and 1 hydrogen. If you were to count the number of particles in each container, you would find that it's the same number for all 3 containers. This is due to Avogadro's law. At room temperature and pressure, 1 mole of any ideal gas occupies approximately 24 decimeters cubed. This volume is known as the molar volume of a gas at RTP. Before further explaining this, let us clarify what is meant by RTP. A room in the UK will have a very different temperature from a room in Siberia, so room temperature has a very specific definition in chemistry. In the context of Avogadro's law, room temperature is considered to be 20 degrees Celsius, or 293 Kelvin, and room pressure is 1 atmosphere, or 1 atm. These conditions are often used as standard conditions for many calculations involving gases. This means that if you have a balloon kept at 20 degrees Celsius and 1 atmosphere pressure and you fill it with 1 mole of any gas, the balloon will expand or contract until it occupies a volume of 24 decimeters cubed. This is true regardless of what gas is inside the balloon. Let's dive into some GCSE level questions to apply our understanding of Avogadro's law. Here is our first question. Suppose you have 3 moles of hydrogen at RTP. How much volume will it occupy? Feel free to pause here to have a go yourself. Now let's go through the answer. First, recall that 1 mole of gas at RTP occupies 24 decimeters cubed. Since we have 3 moles, the gas will occupy 3 times 24, which equals 72 decimeters cubed. Now for our second question, suppose instead of hydrogen, you have 3 moles of chlorine. How much volume will it occupy? Feel free to pause here to have a go yourself. Recall that, according to Avogadro's law, equal numbers of moles at the same temperature and pressure occupy the same volume. Hence, it will also occupy 72 decimeters cubed. Now for our final question on calculating the number of moles from volume. Suppose you have a balloon filled with 48 decimeters cubed of helium. How many molecules of helium would be present inside it? Feel free to pause here to have a go yourself. Recall that 1 mole of gas at room temperature and pressure occupies 24 decimeters cubed. 48 decimeters cubed means we have 48 divided by 24, which equals 2 moles of helium. Using Avogadro's number, this corresponds to 2 times 6.022 times 10 to the 23, which equals 1.204 times 10 to the 24 molecules. In today's lesson, we delved into Avogadro's law and its significance in quantitative chemistry. We explored how Avogadro's law states that equal volumes of gases at the same temperature and pressure contain an equal number of molecules. We discussed how, at room temperature and pressure, which are set conditions we've clearly defined, 1 mole of any gas occupies a volume of 24 cubic decimeters. This fixed volume provides a convenient way to relate the number of moles of a gas to its volume, making it easier to perform stoichiometric calculations in chemical reactions involving gases, as we'll see in upcoming lessons.